How does water boil? I mean, it seems like one of the simplest questions you could ask, right? You put a pot on the stove, you heat it up, and it bubbles. Simple. But what if I told you that understanding what's really going on inside that pot is the key to some of the most bizarre, most daredevil physics you've ever seen? Well, let's dive in and unravel the sizzling science behind this everyday magic.
So we're not going to start in a kitchen. We're going to start with a stunt that honestly sounds like a recipe for a trip to the emergency room. It's a real mystery, one that seems to just fly in the face of common sense.
You heard that correctly. That's a quote from physicist G.R. Walker talking about an experiment he did on himself. He plunged his wet fingers into a pot of molten lead. We're talking lead heated to over 400 degrees Celsius. That's more than 750 degrees Fahrenheit. And somehow, he walked away without a burn.
So this is the big question, right? This is at the heart of our entire explainer today. How in the world can a little bit of tap water protect your skin from something hot enough to melt metal? The answer, as it turns out, is hiding in plain sight. To solve this molten lead mystery, we've got to rewind. We have to go back to that simple pot of boiling water. Because believe it or not, the very same physics that protects a daredevil's hand is the exact same physics that makes your kettle sing before it whistles.
See, boiling isn't just one thing happening. It's more like a four-act play. First, as the water warms up, you see those tiny little bubbles of dissolved air escaping. That's just the prelude, not the main event. Then, the water right at the bottom gets superheated, actually pushing past its normal boiling point of 100 degrees Celsius. And this is where the action really starts. Vapor bubbles start to form, they rise up into the cooler water above, and then they violently collapse. It's only when the whole pot is hot enough that these bubbles can actually survive their journey all the way to the surface. And that's the grand finale, a full boil.
I just love this description. That sound your kettle makes, it's not some gentle hum. It's the clamor of collapsing bubbles. It's the sound of thousands of tiny steam pockets being born and then instantly crushed, each one sending out a tiny little shockwave. This violent, unstable process is what creates the kettle's song.
Okay, and here is where things get really, really weird. You'd think that the hotter you make a surface, the faster water would boil away on it. That just makes sense, but it's not always true. In fact, sometimes making something hotter can dramatically slow down the boiling process.
G.R. Walker shares this fantastic story from his childhood. His grandmother had this perfect test for her pancake skillet. If she flicked a drop of water on it and it just sizzled away in a few seconds, she knew the pan wasn't hot enough yet. But when she got the pan even hotter, the water drops would suddenly beat up and skitter around, dancing for a minute or even more. That's when she knew it was perfect. So think about that. More heat made the water last way, way longer. How is that possible?
Well, this scientific chart, which is called a boiling curve, shows us exactly what Walker's grandmother observed in her kitchen. So follow the curve with me. As the surface temperature goes up, the amount of heat transferred to the water goes up, but only to a certain point. Then, something really strange happens. The curve actually dips back down. In this transition area, as the pan gets even hotter, the heat transfer gets worse. The water drop is now so insulated from the heat that it survives for much longer. And that sweet spot, the temperature where the drop lasts the longest, is called the Leidenfrost point.
This strange phenomenon, the secret behind both the dancing water drops and that insane molten lead stunt, it has a name. It's called the Leidenfrost Effect, and it's all about creating an invisible shield made of nothing but steam.
Okay, so here's how it works. When a surface is extremely hot, way past the boiling point, the very bottom layer of the water drop instantly flashes into steam. The pressure from this vapor is actually strong enough to lift the rest of the drop completely off the hot surface. The water is literally floating on a cushion of its own vapor.
And get this, the shield that gives us incredible protection is ridiculously thin. We're talking about a layer of steam that is thinner than a single sheet of paper. You see, water vapor is a terrible conductor of heat. So even this tiny, tiny gap is enough to dramatically slow down the transfer of energy from that hot skillet to the water drop itself.
So let's just put it all together side by side. On a moderately hot surface, the water makes direct contact. It sizzles, boils like crazy, and it's gone in a flash because the heat transfer is super efficient. But on a very hot surface, one that's past that Leidenfrost point, there's no direct contact at all. The drop floats, it dances around, and it evaporates very slowly. All because that little vapor shield makes heat transfer incredibly inefficient.
So, now that we understand the whole invisible shield thing, let's circle back to G.R. Walker and his, well, let's call them foolish demonstrations. Because the Leidenfrost effect wasn't just his party trick with molten lead.
You know, the same exact principle works in reverse. Liquid nitrogen is insanely cold, right? Like minus 200 degrees Celsius. But your mouth, by comparison, is incredibly hot. So when liquid nitrogen is poured into the mouth, a protective layer of nitrogen gas instantly forms, preventing the super cold liquid from actually touching your tongue.
But, and this is a really big but, make no mistake, just because you understand the physics does not make these stunts safe. That nitrogen demonstration, it thermally shocked Walker's teeth and actually cracked the enamel. And remember the lead stunt? He once tried dipping a dry finger in, and he felt immediate, intense pain. Why? Because with no water, there's no Leidenfrost effect, no protective vapor shield.
Walker himself is adamant about how dangerous this stuff is. If the lead is too cool, it can solidify around your hand, which guarantees a horrific burn. If you use too much water, it can cause a steam explosion, blasting molten lead everywhere. Walker himself got scars on his face and arms from those explosions. His final conclusion is simple, direct, and unambiguous. You should never repeat this demonstration.
But let's end with Walker's humorous take on the power of physics, which he also applied to firewalking, another thing that relies in part on the Leidenfrost effect from sweaty feet. He half-jokingly suggested it should be the ultimate final exam for physics students. It's a funny idea, but it highlights a much deeper truth. Physics isn't just a bunch of equations in a dusty textbook. It's a description of reality. And having a strong belief in it, a really deep understanding of how it all works, can explain things that look like pure magic. And maybe, just maybe, it can even protect you from getting burned.